T-minus 10, 9, 8, 7, 6, 5. All three engines up and burning. 2, 1, 0, and liftoff.
Welcome to the Citizens of Tech podcast. Today we have a special. Gravitational waves have been making the news lately because they have been actually detected. They've been theorized. We've seen indirect results of gravitational waves, but now they've been actually detected. And Eric landed an interview with Dr. Harold Geller, who knows a lot about this particular topic and gave us about a half an hour of his time for the discussion. Who is Dr. Harold Geller, you might wonder? Well, we took some notes from Amazon, and he is a lot of things. So here's some highlights. Currently, his title, Observatory Director and Associate Professor at George Mason University in the Department of Physics and Astronomy. He served as co-Investigator, STEM team member, and consulting scientist for the Virginia Initiative for Science Teaching and Achievement. And I'll just pick, we could go on and on for a long time talking about who this man is and what his accomplishments are, but just a few things. In 2012, named as Solar System Ambassador for the NASA Jet Propulsion Laboratory. In 2008, he was awarded the GMU Faculty Member of the Year, and he authored a book titled Astrobiology, the Integrated Science. And then if we look a little bit further in his past, he was the president of the Potomac Geophysical Society, an award-winning tour guide and lecturer with the NASA Goddard Space Flight Center. And even, just to give you a sense of how long he's been doing this, producer of 2 educational multimedia CD-ROMs, which when Eric and I saw that, we were like, oh, that's a blast from the past. Educational CD-ROMs, yeah. So, in all sincerity, it really says just how long Dr. Geller has been at his craft and his expertise and sharing his knowledge. So, we were very privileged to get some of his time on the show today. And without further ado, let's kick off the interview.
So, when we talk about gravitational waves, my understanding of them is that there is, obviously mass affects space-time, right? It bends it. In this case, I guess it causes ripples in it. Is that an accurate description of what a gravitational wave is?
Well, the gravitational waves is like the ripples in a space-time continuum, like that in water, say. But as far as what I like to use as an analogy with my students is the fact that the gravity in the conceptualization by Einstein in his general theory of relativity was able to establish that it's just an effect on the three-dimensional and really four-dimensional space-time continuum. The fourth dimension, of course, being time. But the three space dimensions. And the visualization I use with my students is like a rubber sheet or a piece of latex with a weight set down in it. And so that dimple, I used to use the analogy, you guys remember the hanging chads of the 2000 election?
Yeah, sure do.
The problem I find with today's millennials is, I use that analogy, for example, in a class I just did, they didn't know what a hanging chad was. So that really makes me feel old. I mean, to me, that was like, just from 2000, it's not long ago, but to these, they call them millennials, my students in undergrad astronomy are basically 18 to 22, and they did not understand that. I just have to stop using the hanging chat. But it really is a nice example of the effects of a mass on space-time. And Einstein demonstrated that mathematically we can use that analogy, and that if you have 2 masses close together, in particular revolving around one another, that they will generate ripples in the space-time continuum. So basically, if you just have one mass with nothing else in the universe, you're not going to have gravitational waves. But you do have gravitational waves when you have, in particular, 2 very massive objects, in particular moving at very high velocities. Einstein's general theory of relativity really was first provided evidence in 1919, and there's been evidence from 1960s And what I like to point out, I don't know if your research showed this, in 1993, there was a Nobel Prize given to Russell Holst and Joe Taylor. And I'm really afraid that was somewhat overlooked in the media splurs about the recent direct detection of gravitational waves. So those gentlemen, almost 20 years earlier, by the way, had detected a pulsar, which was a binary pulsar, literally two very massive objects orbiting one another. And because of the slowing down of the signal of the pulsars, that was indirect evidence. So again, the evidence for gravitational waves really goes back to I don't know the exact date, I don't have that in front of me. It's in the 70s. Sorry, I don't know exactly when. And they won the Nobel Prize for the first indirect detection of gravitational waves in 1993. So here we are now, 23 years later. And I do understand the great excitement of the direct detection of gravitational waves. But, we really had a lot of, knowledge beforehand that would lead us to believe that Einstein was correct.
So it's one of those deals where we sort of expected that this would happen at some point, but we didn't know when, and we sort of already knew that this was, as far as we could tell, due to indirect evidence, we knew that this had essentially verified Einstein's theory from back in the early 20th century, and we were just sort of waiting for the first direct observation. Is that accurate? Okay.
Yeah, that's right. Because technologically, it's very difficult to measure directly gravitational waves. And it does open a lot of possibilities. And, I'm not trying to in any way, shape, or form downplay what they've done. This is a great achievement and a great advancement technologically. But as far as it being any kind of surprise or anything, you're about, what did I say? I don't know the exact year in 1970 something. You're about 40 years late. And again, they already awarded a Nobel Prize for discovering gravitational waves. So you'll forgive me if I say the media didn't do due diligence, in my opinion, in presenting the whole picture relating to gravitational waves.
Sure. So this is sort of a big deal to people who haven't been paying attention for the last 20 plus years.
Correct.
Okay. Now, one of the other things that I'm wondering about gravitational waves is, and I did not see this in the limited amount of research that I was doing in preparing for talking with you today, but am I correct in my understanding that there's no medium required here because space-time is the medium?
That's correct. Space-time is the medium. It's, it's not like you need water or air or anything like that. Like electromagnetic waves, gravitational waves propagate in space, if you want to call it, the three space dimensions, and they travel at the speed of light, just like electromagnetic waves.
Okay,
so
and that was my next question. That's perfect. Because when this was directly observed back in February of 2016, it was observed merger event called GW150914, and apparently this is two black holes orbiting each other at 400 megaparsecs, which is 1.3 billion light years away. So my question was, and I guess you just answered it, when they observed it, were they seeing, quote unquote, observing something that happened 1.3 billion years ago? And it sounds like yes.
Yeah, roughly. There's actually a slight difference. Once you get to those distances, the amount of time it took the signal to get here is not exactly the same as its distance. It has to do with what's called look-back time. If you're talking about a few million light years, basically you can say, a few million light years away means we're seeing the light a few million years later. But then there is this situation where the space-time continuum itself, space-time is expanding as the universe ages. So you have to take that into consideration. So actually, you're getting, light. There's a slight difference in the calculation. I do this with my own students. I have a table, if you wanted to see the difference between what we call look-back time and the distance. They're not exactly the same.
But even though they're not exactly the same, we're still talking about a length of time that is very long in the past that this
As I
event
said,
happened, right?
if it's below about 1 billion light years, you can effectively round off and say, it's 800 million light years away. It's about 800 million years ago that this occurred. But it does differ as you get further and further away, because you have to take into consideration the expansion of the universe as demonstrated by Ed Hubble himself.
So the discrepancy becomes larger, the larger amount of distance, basically.
Yes, correct.
I guess one of the questions I had, and I don't know if you have direct experience with these particular methods, but I was wondering if you had information on how we detect them, because looking at Wikipedia and a few other locations, it looks like there's a number of ways to detect them that have been developed over the years. The first was apparently the Weber bar. There's a spherical version of the Weber bar called Mini Grail. They all involve highly sensitive, highly cooled, generally supercooled substances that then are insulated from regular terrestrial vibrations and so forth.
Basically, with the Weber, I know that was in the 60s, a long time ago. And, again, you've got to remember, you really need very heavy masses with high acceleration velocities and high acceleration and velocity associated with it in order to cause this ripple in the space-time. And so when you're trying to do it in just a big mass, a big bar, or even if you circularize the bar and get a full, very high mass, it's just very difficult. Just think of it just like regular water waves. I mean, how much more difficult it is to see, very small waves versus larger distortions. And so you can imagine the difficulty. That's why I say it's a tremendous technological achievement. And no, by the way, I'm not. My specialty is not in the gravity wave detector business whatsoever. But trying to come up with an analogy of why that's the case. That you need something that can detect very small changes in very large masses. The vibration of very large masses, very small changes. And so, I'm most familiar, and the way the LIGO works is known laser interferometry. And that allows you, it's interferometry that allowed us to measure the speed of light to the highest accuracy back in the late 1800s. And so it's a very precise technique that just goes to show it is so difficult to use this type of technique to see these changes. Also, one thing I do want to say, even though the announcement was made just last month, I don't know if you're aware, but there was inklings that this was successful back in September. There's the engineers first go through and see that the equipment's working. Then they turn it over to the scientists, say, okay, now you do your measurement. They kind of let the cat out of the bag a little earlier. This is not, again, that's why, this great achievement, great announcement. The guys did a great job, no question about it. But as far as the, media hype that was laid to this, it's like people weren't paying attention.
Right, because the information was actually sort of known even 4 months before this announcement back in February.
Right.
Gotcha. Yeah, so in speaking about the interferometer, LIGO, how is it? LIGO, okay. So yeah, it's a laser interferometer that actually, I guess it has 3 facilities based on my reading, but they have light storage arms that are 4 kilometers in length. So I guess that sort of puts in perspective the difficulty in detecting these, because we're talking about very precise measurements, obviously, and the larger. I guess the way that I'm thinking about it is it's almost like trying to tune shortwave radios with certain length antennas, where you have to have a proper length antenna to detect the wave.
Oh, that's a good analogy. I mean,
Okay,
you got it. That's a good analogy.
So because we're talking about, I mean, 4 kilometers for the light storage arms. That's a massive piece of equipment, really. And then there are
Well,
multiple
that's why it
facilities.
costs so much. I
Yeah,
know there has been reports, and I saw some of the complaints, the fact that this program has cost since its inception, which is really, I think in the 80s, someone had said earlier, but as far as I know, this was really started by Kip Thorne and some others. Kip Thorne, I believe, is a Caltech physicist, and that was in the 80s. Some references I did see said it was even earlier, but again, you're talking about money spent over this period of time, which is some 30 years, and what I understand. And, it's about $1 billion in 30 years. And I know the LIGO office itself tries to say, well, the Defense Department spends $600 billion in just 1 year, and $1 billion over the 30 years is not so bad. Somehow today we try to put a price tag on everything. The amount of material that we learn and that we've achieved technologically is just, an order of magnitude beyond what we've done before, and it's just a great achievement, and that part is true.
yeah. It seems like advancements are coming faster and faster in many regards in science. So then there's also talk about space-based interferometry, and they're building or developing, I shouldn't say they're building necessarily, a few space-based interferometers. I guess the technology behind it, they're obviously not up there yet. I presume that would be the same concept, but in space, so less interference and higher sensitivity, greater distances. Is that?
If you have a very long distance and a small change at one end makes a larger change at the far end. Think of that. The longer the distance, the greater mechanical advantage of a lever. This isn't how, of course, it really works, but the analogy is the longer the lever that you have, the larger object you can move.
The classic, give me a long enough lever and I'll move the world, right?
Move the moon. That was what Arthur
The moon, okay, yep.
It would move the moon if you had a long enough lever to do so.
Yeah, so that makes perfect sense.
Small change due to this gravitational wave can be detected if you have an extremely long path length for the light.
So then I guess the only other real question that I specifically had was, what does this mean for the scientific community? I mean, obviously, like you said, this is not shocking news to anyone that is in this realm of research, right? It was expected. It's been indirectly observed before, but does the direct observation specifically mean anything to the scientific community, and specifically astrophysics or what have you? Or is this pretty much, we finally got the evidence, the direct evidence, but not much has changed?
It's like opening up another window in the electromagnetic spectrum, if I can use that analogy.
Okay.
It's like with Hubble Space Telescope, you're in really the visible portion of the spectrum of electromagnetic waves. Now with the James Webb Space Telescope coming in, some people forget it's not the same as the Hubble Space Telescope. That's geared to look into the infrared portion of the electromagnetic spectrum. So by being able to detect gravitational waves, we're opening up a whole new field of detectors that can detect things taking place, as you noted, billions of light years away. And so it really, the better we get at this, you really have a whole new field available to you that, who knows what it will really tell us. So just as radio telescopes opened up another portion of the electromagnetic spectrum, gravitational wave detection has the ability to open up a whole new window on the universe.
And it may lead to other advancements that no one's obviously thought of yet, etc.
Yes, if there are some string theorists who actually believe that if you can modulate gravitational waves, you might be able to communicate with other universes within what they call the bulk. that gets more into string theory and cosmology, but just to give you an idea, that would be wow, right?
Right, yeah, communicating
with
across the
basically
multiverse.
another dimension, yeah.
Right. Wow.
And
yeah.
so, yeah, it can really be something. If I may
right.
say, there is another analogy that's going on that a lot of people are overlooking. We recently completed a neutrino detector at the South Pole Station in Antarctica. And that's actually another window on the universe that gives us another way to look at the universe.
Ultimately giving us other methods to explore more of the characteristics of our universe, right? Because so much of it still remains an enigma that we're trying to understand.
The people with the neutrino telescopes talk about the possibility of learning more about the interior of the Earth, because neutrinos can pass through a lot of material without being affected. So we can have neutrinos pass through the entire Earth, and then slight aberrations in how they refract passing through the Earth will tell us more about the interior of the Earth. That's for neutrinos. And to be honest, we don't know exactly what we're opening up with gravitational waves. It's a little more complicated than even the neutrino.
Sure. Yeah, it gives us another tool. What we can end up doing with it still probably largely remains to be seen.
Correct.
Probably in that same vein, as you were speaking about, what this means as far as it being another tool in the tool belt, as it were. I'm wondering if there's any implications for cosmology and the origins of the universe, etc.
I'm afraid the theory is still way ahead of us, right? Remember, Einstein came up with the general theory of relativity in 1915. I don't think the papers didn't get published until 1916 in English due to something called World War I. And then, British physicists got into it in 1919, doing the first verification of the bending of light due to massive objects. And then, just proceeding from there, we still, this general theory of relativity, in a way, was, say, 100 years ahead of its time, in a sense.
Yeah.
And we are now getting to the point of agreeing with this gravitational wave, even though, as I said, really about 30 to 40 years ago, we had the first indirect evidence.
Yeah, so ultimately, like you just said, we're still sort of catching up with the theory in a way. And so with direct observation of gravitational waves, I guess that lends yet more credibility to the theory of general relativity.
Yeah, it's just another notch in its belt in a sense. It is not, as I said, really a great surprise. And the theorists are already ahead of the curve with string theory. And, I'm not saying that it really will be a way to communicate with another dimension. That's just one theorist's view from the string theory community. But we just don't know yet. And we have not caught up, I hate to point this out to my string theory colleagues, but there's no direct evidence for string theory at this point. Well,
right. Sort of a lot of speculation and some interesting observations, but...
And very useful mathematics. They have developed mathematics that has really helped in other fields as well, no question about that. But again, if you were to ask an experimentalist, hey, they've got no experimental data to uniquely support string theory. So is it a valid theory, or is it just conjecture at this point? It is really something that's debatable.
Yeah, I know it's an ongoing debate, and there's, if anyone pays any attention to the, sort of debate back and forth, there's always sort of a fencing match going on, generally very good-natured, but at the end of the day, even if string theory is not, proven, is a terrible word for theories like this, but if there is no validation for the theory, like you had just said, I think, just the exercise of coming up with the theory and doing the mathematics and all the developments that happen as a result, it's never a bad thing to try to validate things. And the amount of information you can learn as a result, I think, is reward enough in many cases.
Sure. And again, as I said, string theory still relies on general relativity. In fact, if there were no such thing as gravitational waves, string theory collapses also. So general relativity better be correct up to this limit that then string theory takes over.
Right,
You know,
because
it's just like Einstein didn't throw out Newton's theory. He just made it more accurate, more precise.
nuanced, yeah.
Okay? And, you know, if you collapse Einstein's general relativistic equations, you come out with Newton's theories, with the same mathematics that Newton had. It's just, if you are trying to approach higher masses and higher accelerations, you need relativity.
Mm. And then at the macro level where general relativity seems to break down, I guess, is where string theory comes in to try to explain what doesn't make sense.
That's right.
Currently.
So general relativity breaks down, you know, well within the event horizon of a black hole, and that's where string theory picks up. So, you know, it's not that it's getting rid of general relativity, it's just taking it to the next level. And as I said, if gravitational waves were never detected, not only would that have a problem for general relativity, but string theory would be devastated.
String theory relies upon the idea of vibrations in everything, right?
Yeah,
Is my understanding accurate?
Of interactions with virtual particles, in this case talking about graviton, but gravitons are the carriers for, you know, gravitational waves, and if they are real, gravitational waves must exist.
A graviton, again, forgive my elementary understanding, but a graviton being the theoretical particle that gravity acts upon. Is that accurate? Or
I wouldn't say that. It is the virtual particle that carries the gravitational force, just like light carries electromagnetic waves. Gravitons, in a sense, are the carriers for gravitational waves.
Oh, perfect. Okay, yeah, that makes sense. Excellent. Well, that's all the questions that I specifically had. This has been fascinating. I've enjoyed this very much. Ethan, did you have any other questions?
Well, Harold, in closing, did you have a blog or anything with social media that you'd like to mention where people could follow you or your writing that you might be doing?
Yeah, I actually do tweet, and I am AstroBioProf on Twitter. AstroBioProf. Astrobiology is what I teach here and I've written about, and that's my major emphasis these days. So that's my handle on Twitter, at AstroBioProf. And I do tweet not only about astrobiology, but basically about all things science.
Well, Eric, that was a pretty fascinating interview. Lucky that you were able to get a hold of Dr. Geller, Harold as he preferred to be called, and that he was able to give us some time. I knew very little about this topic, so was there any one thing that stood out to you?
I guess the biggest thing that stood out to me was his description of what this means for science. You know, a lot of it remains to be seen what this means for science, but it's one more tool in the tool belt for observation of, you know, the cosmos, the universe, as we, you know, have limited understanding of it and are trying to gain more understanding. So having more tools is always a good thing when you're trying to solve a puzzle. I guess that's the biggest thing for me.
The thing that stood out to me was along those lines. One, what does it mean for science? And the answer being, we kind of don't know. But two, remember he was describing how it was like an object or a mass that has gravity kind of bends, you know, time like a ball in a rubber sheet. I think he described it that way, roughly. Okay, so I have seen that illustration before, and that really resonated with me. I got that. So now, okay, we're at this point where we can detect these things that were formerly only a theory and described generally. Now we can actually detect the waves, and then he said, well, it's kind of like we could now see infrared light and we can now see other parts of the spectrum we didn't know were there. It's sort of like that. No, it's not light spectrum exactly, but we've just enabled seeing a whole new thing that we didn't used to be able to see. And what is that going to tell us about the universe? We don't exactly know. It reminded me of a Nova special I saw recently about phosphorescence under the ocean in a whole bunch of critters, naturally occurring bioluminescence due to protein genes that are activated in certain creatures. When you look with the right lights and the right filters, you see a world you never saw before. And this is what I'm thinking is gonna happen here. Now we've got the means to detect gravitational waves. What will that teach us about the universe? And as you were getting into the conversation at the end about string theory, it could prove the validity of string theory, and then take us even further into our wild fantasies and notions about the multiverse, which does seem like the stuff of science fiction. All of a sudden, being able to see gravitational waves, we don't know, but maybe it's going to be the tool that is instrumental in proving the existence of these things, and then taking the next step towards communicating with them, as he said. Again, he didn't say it's going to happen. It was just one guy's idea from the string theory community. Maybe we could communicate with the multiverse. Wow. That's pretty awesome.
Yeah, or at the very least, maybe it's the tool that helps you build the tool that makes that happen.
Exactly.
So it's,
right.
Yeah, it's awesome to talk with someone that has that viewpoint. It was really, really a great time.
Well, Eric, how can people follow you on Twitter?
You can follow me on Twitter at Zutphen, Zutfen.
Which is also the name of your blog?
That is the name of my blog, Zutphen.com.
And I am Ethan Banks, at EC Banks on Twitter. EthanCBanks.com is my blog. And, of course, this is the Citizens of Tech podcast. You can find this show and all our shows at citizensoftech.com. And, of course, we're on iTunes. And if you would, give us a review. You'd make us feel really good about ourselves to know that you love our show. And if you don't like the show, hey, shut up about it. We don't want to hear from you at all. Not whatsoever.
Only tell us good things.
That's right. Tell us what we want to hear. Thanks, everyone. We'll see you next week.
Take care.